Now it's my privilege to introduce Dr. Daniela Roos. She's the director of our partner in this symposium, the Computer Science and Artificial Intelligence Laboratory. She earned her PhD in computer science from Cornell, and her research interests include mobile computing, data science, and integrating robots into our lives in a way that improve our quality of life significantly. So please help me in welcoming Dr. Daniela Roos.
Hi, everyone. Apologies, it's taking me a little bit to get to the chair. I broke my ankle not too long ago. Let's see, I think I have the wrong screen in front of me. Can you make sure that I get the right screen in front of me? It's supposed to be a different screen. Can you work with the guys in the back? So let's see. So today, we have extraordinary automation in manufacturing. We have robots that help with packing of factory floors, and we have 3D printing that creates customized goods. We have network sensors that enable, can you please fix this? We have 3D printers that create customized goods, and we have network sensors that, that enable us to monitor everything in the process at the factory. And all of these opportunities are getting so much more substantive with AI, machine learning, and robotics technologies. But this work is happening in the context of several waves of automation. So the first wave of automations brought up these extraordinary robots, these extraordinary machines that are so much better than humans at executing precise operations. But these machines can only do fixed tasks, and they remain isolated from the people on the factory floor because they're huge and dangerous to be around. What we would like is to make progress, and in fact we already have made progress. We have the second wave of automation that's bringing us suction cups, drones, and the ability to move in an automated way on the production line. This is still wrong. We are now in the third wave of automation. And this third wave of automation is giving us the ability to do increasingly more complex tasks. So the question is, what can we do with robots and AI and machine learning? Well, these technologies are actually enabled by three interconnected fields. We have on one hand robotics, which puts computation in motion and gives machines the ability to move. We have artificial intelligence, which gives machines the ability to reason, to execute language models, to make decisions. And we have machine learning, which cuts across the two domains and enables machines to learn, to improve, and to make predictions. For manufacturing, these technologies connect together to ensure advances in productivity in so many ways. On one hand, we have the ability to use data to do process optimization. On the other hand, we have the ability to use data from sensors to do predictive maintenance. We have the ability to use the supervised information from our systems to increase the quality of the products that we create. We can do inventory management, we can do supply chain optimization, we can do customized design, we can do so many different things that allow us to ensure that we introduce optimization and efficiency in our processes. And all of these capabilities are enabled by machine learning. Now, machine learning is a broad term that refers to a wide range of algorithms. And machine learning typically starts with data, and then the data goes through multiple steps. There is an algorithm that labels the data, then there is a model that gets trained using the data. There is a prediction that comes out of that model, and then there is ultimately a decision-making step by the humans. And today we have three types of machine learning that could be broadly deployed in manufacturing. We have reinforcement learning. So we have machine learning that effectively gives us reinforcement learning. We have machine learning that effectively gives us pattern recognition. And we have machine learning that effectively gives us generative AI. So the timer is not working. All right, so here's the reinforcement learning idea. So in reinforcement learning idea, the basic idea is to provide human input to select between good decisions or bad decisions so that the system optimizes a cost function that gradually over time drives the system towards the good decisions. And so here you can see an example of reinforcement learning where a group of agents is learning how to move on a track. You can imagine this track as being a loop in a warehouse, for instance. And you can see that there is a lot of this is a whole bunch of machines that are trying to learn how to drive fast on this track. And the idea is that through trial and error, the machines actually learn how to turn corners. So that's essentially the idea behind reinforcement learning. Now, the other category of machine learning is for pattern recognition. And in this category of machine learning, the idea is to really think about what has happened, to use data to think about what happened in the past, what will happen in the future, and what should I do. And typically, these machine learning solutions are provided by methodologies called deep neural networks, where a large network is trained using labeled data. For instance, in this case, you can see labeled data that says, oh, this is a picture that shows screws, bolts, and nuts. And these systems are huge. They have usually millions of artificial neurons and even more parameters. The parameters are the edges between the neurons. And so here the objective is so that when a new image gets presented to the network that the network hasn't seen before, the model can then say, this is a picture of a bolt, because it looks a lot like other pictures of bolts that people have shown to the system in the past. So there is a lot of opportunity to use these kinds of ideas to identify what is happening on the production line. So the third type of machine learning is something that you have heard a lot about in the previous conversation, and this is about generative AI. And in generative AI, the idea is to kind of still do a classification, but now we want to do the inverse of a classification. So in pattern recognition, we look at the pattern and we say, this is a picture of, let's say, a bird. But now in generative AI, we want to start with a notion of a bird and generate a new pattern. And here what is hard is that this is no longer a one-to-one function, because birds could come in so many different kinds of shapes, colors, orientations. So which bird do we want? And so the way we model that with generative AI is by introducing a kind of a noise or a probabilistic tunable set of parameters. You can think of them as dice. And so the idea is that by picking different rolls of the dice, or by tuning knobs in different ways, we can select for different types of properties of the birds. And in fact, these birds can be tunable to the types of processes that we care about. And so you can think of these parameters as sort of continuous knobs that when you jiggle them, when you turn them, you can pick a different color or a different orientation or a different size. And so that's essentially the intuition behind how we can go from a concept to selecting a particular type of object that corresponds to that concept. And these parameters represent continuous functions. Depending on how we select for them, we can pick any of the birds that you see here on the screen, where some birds are in with a different background color, some birds are in different orientations. And so then the question is, how do we actually train these generative AI models in order to deliver this kind of capability? And the answer is we use a lot of data, but it's actually really hard to think about introducing noise as part of the model. So it's really difficult to think about how do we go from concepts to noise. It's actually, or how do we go from noise to concept? So what this particular noise, what kind of concept does it represent? It's much easier to go the other way. And so, for instance, if you think about each of these examples as a kind of a colorful balloon that you pop, and then all the little particles start diffusing, you get gradually more and more noise or an increasingly noisier representation. Now what we want to do is to think about putting all the bits back into the shape. And so this is effectively what we do in order to train our generative AI models. Because once we have supervised what shapes correspond to what noise, it's possible to go from a certain noise pattern to a particular shape, because different shapes result in different noise patterns. So this is pretty exciting, and intuitively at the high level, this is how generative AI works. I want to give you an example to show you how this kind of performance really depends on the quality and the size of the data. And so this is a picture that was generated by my students using a generative AI model. They trained this generative AI model on 5.8 billion images. That training took about 3 months. And once they've trained their model using essentially the algorithm I have shown you, they were able to instantiate that model for me by selecting 10 random pictures of me from the internet and doing another couple of hours worth of training. And at this point, the trained system can generate any picture that resembles me. So this is one of them. And this was done in classical painting style. So you can add constraints to how you use the systems. You can also use these kinds of approaches with other types of data. So here you can see a large language model that I asked to write a poem about the use of AI in manufacturing. And it took about 10 seconds for the system to generate the following. So in the factories of modern day, machines and tech rule the way. AI joins the fray to lend its aid, and manufacturing is forever changed. And it goes on like this. It's pretty good, right? And so it turns out that you can use these techniques. You can use deep learning. You can use generative models. You can use reinforcement learning on a wide range of problems. And I want to show you a few examples. So this one is so this first example shows you how you can use these systems to essentially select for particular characteristics in an environment. So this is a design, this is a creative design approach, if you want, that's driven computationally, and it's tasked to generate designs that meet different types of specifications. So this one is get me the fastest design that can move on a flat surface. This one is a different one. It's for climbing stairs. And and so the first one, if you recall, was jumping over gaps in the terrain. This one is yet another one that is able to go over rich terrain. So you see, you have the ability to tune the systems with specific constraints that give you the ability to come up with designs optimized for specific needs. And once you have the designs, you can then create them you can then go from physical design to a physical object because the designs can be fed through simulation systems that can check whether they meet their the specifications. So in the previous example I have shown you, you had the design, but then you also had the simulation to verify what the performance of that particular design was in the context of the task. And you can come up with a lot of really creative ideas using these types of approaches. So this is an example of a new type of robot gripper we call the origami magic ball gripper. It's a very unique gripper. It's not what you see on the manufacturing floors right now, but it's a gripper that has a very great properties. So it's a very light gripper with high payload. This gripper weighs on the order of a few grams. It can lift between 100 and 1,000 times its weight. And it's also very compliant and adaptive to the parts that it needs to pick up. It does not need to know exactly the geometry of the object it needs to manipulate, nor its precise location and orientation. And so you can use generative AI approaches to come up with out-of-the-box ideas that deliver this kind of performance. You can also use generative AI ideas to do other tasks on the manufacturing floor. So this is an example where we're using machine learning. Actually, this is not generative, this is deep learning. We're using machine learning to enable human-machine collaborations, human-robot collaborations, where the robot adapts to the person. And in this case, we have sensors that are installed on the person. They are simple and wearable. And with these sensors, the system can actually monitor the muscle activities, and then machine learning can help the system differentiate between the type of action that the person is executing. And so, for instance, can you hit play on this video? The video is not playing. Can you hit play, please? So in this case, you can see a human and the robot collaborate. Can you please hit play? You can see a human and the robot that are supposed to collaborate together in order to lift this object. And I'm sorry, we are having technical problems. Oh, it's playing. Oh, it's not playing in my screen here. So yeah. So you see here in the stage, the machine learning system communicates to the robot that now it has to be limp to kind of follow the person. But at some point, when the person lifts the blanket and stiffens the muscle, the robot also stiffens the muscle. And this is not pre-programmed. This is all done using machine learning. So there are many other things that we can do with these systems. I wanted to show you one last example. We're using machine learning and using a method to detect brain activity, in particular to detect whether the person has the brain signal that indicates there is an error. The system can be used to actually indirectly supervise and direct the robot. So in this case, this robot is supposed to sort paint cans and wireframes in different bins, and when the robot moves to the wrong bin, the system detects brain activity as, oh, that's the wrong bin, and then immediately can direct the robot to the other bin. So it's really extraordinary what you can do with machine learning today. That task requires machine learning because it's not possible to do the kind of complex classification that comes out of such a lot of data using direct algorithms. And so let me close by observing that advances in AI and robotics and machine learning are really promising a very great future for the manufacturing industry. Not only can we introduce efficiencies and optimizations, But we can also imagine a future where the manufacturing jobs get better, where people, instead of being the actual workers on the factory floor, where people can be the supervisors and the people who configure the manufacturing lines on demand in a way that enables customization and enables more range in the products that can be developed. And with these kinds of approaches, we can imagine changing manufacturing from where it is today, where we have fixed manufacturing at fixed locations and we produce fixed products. We can imagine making the manufacturing production much more customized and much more localized. And so let me close by saying that the future of manufacturing really depends on a few important points. So first of all, we need scalable data sharing and education tools that enable these kinds of benefits. We also need AI tools to enhance the supply chain discovery and the ecosystem resiliency. And we need AI and business models for manufacturing. And we need to develop both the technology behind these aspirations, these objectives. We also need business models, and we need the right incentivizations. So ultimately, with machine learning, with AI, with robots, we can innovate, but this actually requires an infrastructure that supports computation and data. It also requires the workers that are ready for these kinds of packages and activities. And we need to increase the cultural agility at the workplace so that new technology can be adopted faster. Thank you.
Thank you, Daniela. Oh, sorry. Thank you, Daniela. Sorry about the time mix-ups. Right now, it's 11:04. I don't know if you have time to take a question.
Maybe we can take a couple questions, yeah.
Okay.
Quick ones.
Great, thanks. I loved your speech. At least where I work in the past, the quality of data has been a huge challenge. Either we're missing data or the data that we do have is inaccurate in some ways. To what degree can generative AI be used to kind of plug these holes, to fill in these gaps so that that becomes less of an issue?
Well, in theory, this should be doable. In practice, it really depends on the training data. And it depends on how we incentivize the manufacturers to collect and share the data. I want to remind you that the portrait I have shown you was trained on 5.8 billion points. So how do we get to that level of data? For today's solutions, scaling up the data is absolutely necessary. In fact, Sebastian Bubeck of Microsoft has a theorem that says if we're going to use transformer-based solutions, the only way to get better performance is to scale up the data used to train the system. Now, on the other hand, there is new research that some groups, including mine, are promoting and are pushing forward, where the objective is to think about new models that are not as large as the large language models and that are not as data hungry as the large language models. And so I, for one, am convinced that in 2-3 years' time, we will have great solutions. In fact, just recently, I saw a post from Mosaic ML, which is a startup from MIT CSAIL. What they do is they look at the model that was trained to perform a certain task, and then they prune it. They remove some of the parameters that are not necessary. And research shows that you can get rid of up to 80% of the parameters for not much hit in the performance. So I think that in the future, we will be able to have more manageable, more compact models that could deal with smaller data sets. But for now, the data is the key. And so we need to incentivize people to generate the right data and share that data, because it's inconceivable that an SME will generate 5.8 billion data points for the particular aspect of manufacturing that they're focused on. All right. Well, thank you very much.
Thank you, Daniela.